Well, good afternoon, everybody. It's my pleasure to present the public lecture of our Rothschild Fellow, Professor Molchanov. So just a couple of words. Many of you, of course, know him and his work. Just a couple of words. Professor Molchanov received his PhD in Moscow State University, received there 2 dissertation, PhD, and then full Doctor of Science. Worked mostly in the Moscow State University and afterwards in Charlotte in North Carolina. Main somehow works of, well, it was saying possibly that he gave talks in all over the world, several times in the International Congress of Mathematical Physics, International Congress of Mathematics. Main works in Markov processes, Martin boundaries, diffusion and Riemannian manifolds, spectral theory, particularly localization in random media. Many discussion and application to physics process and fields in disordered structures, particularly one of the keywords here, intermittency, with application to geophysics, astrophysics, oceanology. Lots of work on wave processes in periodic and random media, quantum graph, application to optics and population dynamics. Professor Molchanov has, I suppose, about 30, 40 PhD students received a PhD in Moscow University and 17 in the United States. There's more than 300 papers and publications in the best journal. And today we'll hear the lecture with very interesting combination of population dynamics and something interesting which is going on the sun.
Okay, thank you. I will discuss several problems related to the non-stationary random media. This topic was the central point of my studies first of all, in the very end of 80s. I worked the time with a group of academicians Zildovich, and the topic was the structure of magnetic field of the sun, and I will discuss something like this at the popular level today. And second topic, in fact, is technically closely related, is the population dynamics. When we have very similar equations and very similar effect, main effect here is the intermittency term proposed by Yakov Zildovich. Intermittent field means field which highly non-uniform. There is concept of homogenization based on the idea that in large scale many fields looks like uniform or almost uniform, and completely different idea. Intermittency means that main contribution to this field give very sparse, extremely high peaks or other singularities. I will start from the black spots on the surface of the sun. The principal understanding about deep relation between black spot on the surface of the sun and climate of the Earth is going to the end of 17th century, when English astronomer Maunder made several very interesting observations. He collected statistics of the solar magnetic field for many, many years, and he discovered that there is strong decay in the number of solar spots, black spots, and to the end of the 17th century, practically there were no at all spots on the surface of the sun. And he supposed that this is the manifestation of some kind of degradation of the solar activity. This period, end of 17th century, beginning of the 18th century, is known as the Maunder cooling. It was probably the coldest period in the history of civilization. In South France, for instance, such rivers as Rhone and Loire were covered by ice during 3 months. Snow covered Germany, Denmark, Netherlands, and this north west Europe for 6 months and more. If you look at the Dutch painting of the 17th century, very famous example is the painting Seasons by Peter Bruegel. It's in Vienna Museum of Art. They showed remarkable winter picture in the countries which forgot about snow today. That's deep snow covers full country, frozen channels and frozen lakes, skating of the children, and so on and so forth. But Maunder, that time, it was in fact, by the way, the time when several very famous persons lived: Isaac Newton, Peter the Great, Louis XIV, and so on. That time, what Maunder made observations that practically all solar spots disappeared. And as I said you already, he concluded that cooling, which called the Maunder cooling, is related closely to this fact. Today's explanation of this phenomenon maybe this explanation is not complete, but I'm talking about point of view of Zildovich on this topic. Today's explanation has the following form: that in the surface of the sun, upper layer photosphere is about 300 kilometers. It's covered by hydrogen in the stage of ionization. And the temperature is very fast increasing in direction to the center, and the plasma, light plasma, wants to go up. This is the phenomenon of the convection. Large-scale convection is again well-known physical fact, is always unstable. And convection form channels in the photosphere. Through some channels, plasma goes up to the surface, very hot plasma goes up to the surface, and after cooling, return to this closely related channel back. And here's something like this. There is magnetic field of the sun, motion of the plasma, because it's the state of ionization, is some kind of electrical current. This electric current generates additional magnetic field, and after this, that we have further increasing of magnetic fields step by step. There is, in fact, in the early stages of this so-called dynamo process, there is exponential increasing of the magnetic fields. But energy of magnetic fields, of course, source of the energy is kinetic energy of the plasma. If magnetic field is increasing, that temperature inside this convection column started to decay. Black spots are black simply because on the surface of the sun, mean temperature about 6,000 centigrades, but on the black spots, it can be only 2,000, something like this. And we see the top area of such convection columns as the black spots. If number of the such convection columns is small, that flow of the hot plasma to the surface is suppressed, and the surface of the sun is much, much colder. And this, of course, affect to the climate of the Earth. Why in the end of 17th century we had this strange, very fast decay of the number of convection columns? Nobody knows. The details of the solar cycle are not clear, precisely are not clear even today. But a simple explanation about this connection, I repeat one more time, is very simple. Small number of the black spot means that we have small number of the convection columns. We have small amount of the hot, of the hot plasma going to the upper layer of the photosphere, and so on and so forth. This is, of course, only general conversation. It's not mathematics. I will try now to explain what kind of mathematics we have here. There is field h of tx. It has three components, of course. We are living in three-dimensional space. And there is velocity field, v of t x. It's again with the component, velocity field of the plasma. This velocity field satisfies some kind of equation of the gas dynamics, but in the Deutsch model of the dynamo process, we exclude inverse influence of the magnetic field on the velocity field. We want to forget about the fact which I formulated, that the energy of magnetic field, source of the energy of magnetic field is the kinetic energy of the fluid. And for the magnetic fields, we have standard Maxwell equation. It's nu sub m times delta h. It is standard usual Laplace operator. Nu sub m is diffusion coefficient, which in fact has the meaning of the electrical resistance of the medium. If temperature on the surface of the sun is very high, parameter nu m is very small. Sun is not very hot star. As I said, you only 6,000 centigrades on the surface, but real blue stars have temperature millions of the centigrades on the surface. And plus curl, and here we have V cross H. And of course, we have some initial conditions, H naught of x, for t is equal to 0. This is a parabolic system. If we assume that coefficient is the field view of tx is sufficiently smooth. If we assume that this field cannot be, of course, bounded, but this field, like Gaussian field, has very slow increasing near infinity. Gaussian field as a distance of r has maximum value for the square root of logarithm r. This is very slow increasing. In this case, there is no any problems to prove existence and uniqueness solution of this parabolic problem. But we are interested in, of course, asymptotic behavior of this solution, but and to understand this asymptotic behavior, we will make additional assumption about v of tx. Let us first of all present this Maxwell equation in the bit different form. If you will open this curl using standard tricks from vector analysis, that we will find that will be nu m times delta h plus I will write down this equation for one coordinate. Let us consider one of the coordinates, h sub I of tx d dt equals nu sub m delta h sub I plus plus d h d x d h I d x j times v sub j summation j from 1 to 3. This is looks like as the drift of the Markov process. This is the Laplace operator correspond to the Brownian motion, of course, but this is the drift minus next term, and in next term we have the coupling between the different components of the magnetic field. Summation d v I d x j h sub j of tx, j from 1 to 3. This is I equals 1 to 3. This is the same Maxwell system, which written in coordinate form. Let us look at the first two terms. This is the generator of some Markov process. We have diffusion coefficient, Laplace operator, and some first derivative term with coefficient. That coefficient, according to terminology, Kolmogorov terminology, is the drift. We will call this L sub hi. This is generator of the some Markov process. Let us introduce psi of t Markov process with such generator. It's possible to write down for this process stochastic differential equation dxit is square root of 2 nu sub m d wt. This is diffusion term containing Wiener process of Brownian motion, and minus the drift v of t psi t dt, something like this. In physical literature, this process, solution of this stochastic differential equation, is called usually Lagrangian trajectory. It's how one particular drop of the fluid moves in the space. But here we have matrix potential dvi dxj. This is 3 by 3 matrix, which we multiply by the vector H. 3 times 3 vectors and vector H is exactly vector. For the solution, if we know trajectory of this process psi of t, we can write down some kind of the Katz-Feynman formula. But this Katz-Feynman formula looks completely different from the usual Katz-Feynman formula, which we apply to the in spectral analysis in many other areas. In everything depends on the fact that the scalar form commutative groups, but matrices non-commutative. We will add to our equation additional requirements. We will assume that divergence of V is equal to 0, and the divergence of H is also 0. Then it follows from Maxwell equation that divergence H naught is equal to 0, but after this divergence of H will be equal to 0 forever. And divergence of V equal to 0 means that summation d I dxi, I from 1 to 3 is equal to 0. It means that this matrix potential, trace of this matrix potential is equal to 0. In other terms, matrix potential V, no, maybe W, I will write down Ij. This is the Di, dxj as a function of t and x. Trace of this W is equal to 0. And we can write down the green function of this equation in the following form. This is the Katz-Feynman formula. We will, first of all, we will find that U of that H of Tx can be presented as expectation starting from X, and we have, if we have function G I J, this is matrix green function of T minus S. What is, I will look at my notes. T X and here psi S or psi T. It's not very important, of course. Times H0 as a point 0 psi. This is but this green function is given by the following so-called multiplicative integral. In the standard Katz-Feynman formula, we have expectation of something, exponent. In exponent, we have integral from 0 to t of the potential along the trajectory of the diffusion process. But here, potential is matrix potential, and the result, this green function is given by the following expression: is a product for S equal to 0 to t, delta ij, unit matrix, minus dv I dxj This is our matrix W, T minus S, psi S. And this product, of course, it has to understand in the, this is a G I J of T X. And of course, here we have mass expectation from X. T X. This is, we have here unit matrix, and we subtract this matrix W in the inverse time. Matrices, this W capital have zero trace. They belong to Lie algebra of the group SL3R. And of course, they are not commute. And as a result, we cannot lift this expression in the exponent. We can write down exponent of this expression for each term, of course. But unfortunately, non-commutativity, we have a serious problem here. And this is not strange. And this is the main technical difficulty. If we have scalar Kac-Feynman formula, which contains an expectation exponent integral from 0 to t, some v of t minus s psi s ds, something like this. It's again can be written, of course, it's very similar form. But this is exponent containing some real number. We have positivity here. We have maximum principle for the scalar Schrödinger equation. We have positivity principle. If initial condition is positive, solution is positive. But here, of course, it is not true. We have vector valued solution H, and in good situation, this solution is isotropic. All directions have the same probability. Direction of velocity of the magnetic fields in each moment t and point x typically is uniformly distributed in space. In this case, of course, we cannot assume any possibility, any positivity. And this is Kac-Feynman representation. It's again, right now it's a general fact. Under some smoothness condition, regularity condition, we can write down all such formulas. But we are interested in to find moments of the H, field H. Our main problem is to find moments of H of Tx. Let us note that I already presented H of Tx as an expectation starting from point X or something else. X is the initial point in inverse time for the our Lagrangian trajectory. This expectation is expectation with respect to Wiener process, which we introduced in our equations, the Huttig differential equation. But velocity field is also random, but we did not make averaging on the velocity field. But now we must take this H of Tx and take additional expectation, this expectation over distribution of the random velocity field. h of tx. We can call this m1 of tx. And if initial condition is homogeneous, expectation of initial condition will be constant vector. This is still vector, of course. Then we can expect that the first moment under some conditions, it's not always true, but typically expectation is constant. And due to the fact that our field in the future will be isotropic, it must be here. The central moment is at the center. The technical tool here is to study the correlation tensor for our velocity field. H sub I of t x1, H sub j of t x2. We have two different points in space, x1, x2. We have the same moment t, and we have different component of our magnetic field. This is the m2 of t, and due to homogeneity, if you assume that initial field H naught is homogeneous, stationary in space, that this second moment in reality will depend on x1 minus x2.
What kind of assumption do you have on the joint distribution of H and T?
As I said you, that we do not want to study the v of tx, equation for v of tx. V of tx is some velocity field. You can assume, like Deldovich is doing always, that v of tx is some Gaussian field.
Independent of H?
Yes. Why not? Like in standard turbulence theory, like Kolmogorov, we can assume that it's Gaussian fields. If it's isotropic, that the spectral measure of this Gaussian field has a very special structure, and so on and so forth. And this field, of course, Kolmogorov field, is smooth as any Gaussian field, is unbounded, but only logarithmically unbounded, and we have no. Look, in the dynamic equation, v of tx is given. There is no inverse influence of the magnetic field on the velocity field. Any real equation of magnetic hydrodynamics must include v cross h. This is so-called Lorentz force. This Lorentz force can be considered the friction. Magnetic field is increasing. As I said, that velocity field must decay. I said only about this fact at the level of the law of conservation energy. The magnetic energy, source of magnetic energy is kinetic energy of the plasma. But we did not include. It means that dynamo equation can describe only initial part of the creation of magnetic fields. Magnetic fields increase, but we can use this equation until, roughly speaking, 10%. Only 10% of kinetic energy will go to the magnetic field. But after this, of course, we have completely different situation. This magnetic field started to increase. When the temperature in this column will reach 3,000 centigrades, that we have equilibrium between kinetic and magnetic energy. This black spot lives several weeks, and after this disappears slowly. but we are interested in the very beginning. Why? Because the central question of this theory is to explain why cold stars have no magnetic fields at all, but hot stars, especially blue stars, have unbelievably strong magnetic fields. Magnetic fields we can study only for the stars containing strong magnetic fields, because how we measure magnetic field of the hot stars. Surface of hot star is covered by hydrogen. What does mean plasma? I said plasma, fluid. This plasma is simply hydrogen. This is the only main component of any star. Hydrogen in the stage of ionization. And hydrogen atom has ground state energy with a simple eigenvalue, and after this there are eigenvalues with high multiplicity. In the magnetic field there is splitting, the Zeeman effect, splitting of the multiple eigenvalues. And you can measure this splitting, and after this you will understand what is the strength of these magnetic fields. For the second, we want to find equation for the second moment. This is possible only in the assumption that what do you have some? Okay, we can find closed equation for the second moment and for the higher moment, and again it was Zeldovich's idea. If we will assume that this velocity field has the following so-called renovation structure, that it's not delta correlated. In the modern probability theory, there is very popular concept of the partial stochastic differential equations. When we have a Wiener process, but not scalar Wiener process, usual Wiener process, but Wiener process in the infinite dimensional space, in the Hilbert space. This Wiener process, infinite dimensional Wiener process, still is non-smooth, and derivative of this field, this infinite dimensional Wiener process with respect to time t, is white noise, and this white noise has some space correlation. The stochastic differential equation in the Hilbert space with respect to this infinite dimensional white noise is SPDs. Krylov, Rothschild, and million other people working in this area. But for physicists, it's not very interesting, because especially if you consider application to the population dynamics, because not all effects can be explained using delta correlation in time. It's better consider short correlation in time. Physicists understand even white noise dynamically. The white noise is not a process in the sense of the distribution theory, in the sense of generalized function. This is a process which has very short correlation, and this correlation we are interested in what happens if such correlation length tends to 0. Let us consider time axis, and let us divide this time axis into small intervals of the length h. And if time t belongs to interval NH n plus 1 H. Then in this case, velocity field V of tx is constant in time, V sub n of x and omega. And for different n, such velocity fields are independent, and their correlation, they are independent, but inside such intervals, they identically equal, they constant in time. And we are interested in situation when h tends to 0. You can write down such equation for the second moment. You can write down, first of all, integral equation to the second moment on the short time interval. And after this, using some probably semi-physical tricks, you can derive final equation for the second moment. I don't want to discuss this technical topic. I want only to emphasize that in all papers in physical literature, which I know, there is no partial stochastic differential equation, because partial stochastic differential equation is only can appear only in the limit when h tends to 0. But we are interested in effect when h is maybe small but finite. I don't want to discuss present equation for the second moment. What is important here, that this second moment has the critical threshold, that if that kappa nu m, this is the diffusion coefficient, which I said you also is the electrical resistance of our fluid. For the hot stars, nu m is very small. There exists kappa nu critical, such that if nu m smaller than nu critical, then this equation, this dm2, then this second moment m2 is a part. This is a matrix, of course. I am not writing down here ij, that I can write down that lambda plus of m2 of t 0, if x1 is equal to x2, this is the expectation given point, it's a variance of our field. It has asymptotic some constant, some mu plus times t. No, some constant ahead. And mu plus is the eigenvalue of some appropriate Schrödinger equation, and it's possible. For small nu m, that is for the hot stars, second moment increasing exponentially, but first moment is bounded. This is a manifestation of the intermittency, and I will give some comments right now. But if nu m is greater nu critical, this is called stars. That's cold stars start from the temperature about 2020 degrees. Our sun is not cold star, but is going in direction to the cold star. 6,020 degrees on the surface is not very high temperature. But of course, to wait transition to the cold star, it requires maybe millions a year, fortunately for us. And lambda plus in this case will be 0. It means that M2 of T0 is bounded. We have the following situation. We have some equation, some evolution equation for the second moment. In the left part, we have derivative with respect to time t. In the right part, we have some self-adjoint operator, but for the vector functions. This self-adjoint operator, for this self-adjoint operator, you can find spectrum, and top eigenvalue of this operator in the right part is a critical point of the analysis of this field. If this top eigenvalue is positive, second moment is increasing exponentially, first moment is bounded. In this case, the conclusion is that all energy of magnetic field will be concentrated in very small volume on the surface of the sun. It's black spots, exactly black spots. No, I want to emphasize third time that reality is much more complicated. Our equation describes only initial part of the dynamic process. But if nu m is large, its resistance, electric resistance of the fluid is large, which means that the star is cold, then dynamic process will not start at all. Cold stars, they have no magnetic fields at all. Like cold planets, Mars, for instance, has no magnetic fields. Of course, mechanism of magnetic fields on the planets like Mars or Venus or Earth is completely different from the mechanism of creation of magnetic fields on the stars. On the Earth, magnetic fields result of the motion of some liquid metal in the core of in the central part of the planet. But nevertheless, cold, that's after cooling of the planet, if there is no motion of this liquid metal in the center, magnetic field must die. And why why we have such kind of effect? I want to explain phenomenon of the intermittency in the following elementary example. Assume that we have lattice ZD, and each point x of the lattice ZD, we have some random variable psi, which depends on the parameter epsilon, and this psi has only two values: 0 with probability 1 minus epsilon, and 1 minus epsilon with probability epsilon. We have, and assume that for different point x, psi epsilon of x, assume that such random variables are independent. We have Bernoulli field. This Bernoulli field has large value with a small probability and 0 with very large probability. Expectation of psi epsilon is equal to 1. Second moment is equal to 1. Let us maybe, I will consider here 1 over square root of epsilon. But if you consider, no, sorry, 1 over epsilon squared. But expectation of psi epsilon squared will be equal 1 over epsilon. It's very, very large. This is typical intermittency. What is the structure of this Bernoulli field? It has very large values with small probability. It means that points when we have such high peaks are very sparse, and remaining value is 0 with probability close to 1. You have sparse peaks, and the second moment tends to infinity. There are situations, especially in population dynamics, when we have very similar equation. When assume that we have psi epsilon of x is equal to 1 over epsilon. In this case, second moment, expectation of the 1 over square root of epsilon. Then expectation of psi epsilon will be square root of epsilon, but second moment will be 1. But if you consider next moment for its expectation of psi cube, then it will be 1 over square root of epsilon. It will tend to infinity. We have intermittency. Always we have different asymptotic for the successive statistical moments. Some moments started to tend to infinity very fast. Previous moments are bounded. This is true also for the in population dynamics. I have no time to discuss real population dynamics. Instead, is remaining how many minutes? 5 minutes. I will say something about famous Kolmogorov KPP model, Kolmogorov, Petrovskii, Piskunov model. This is already population dynamics. And we have in the very beginning one particle, moment t is equal to 0. We started, for instance, from origin, and particle perform Brownian motion, Wiener process with generated delta. X of t is the trajectory of the Brownian motion or Wiener process. Let us write down W of t. But each particle can be splitted during any time interval dt with probability lambda dt. Lambda is rate, can be split in two particles. There is no death of the particles here. As a result, we have here particle field n of t gamma. N of t gamma is the number of the particles, is the set gamma, moment t, if we start from a single particle at the origin, and if evolution of this population given by parameter lambda, splitting lambda. Total number of the particles is growing, in this case, of course, exponentially. But Kolmogorov, Petrovskii, Piskunov proved that main part, 99.9% of the population will be in some circle of the radius r. We depend on t, and r of t is some constant t naught times t. This constant depends on the diffusion coefficient ahead of maybe kappa. I will write down here. On kappa of lambda, there is very simple exact formula. And there is spherical ecological wave, which propagate linearly in time. Kolmogorov, Petrovskii, Piskunov, in fact, had in mind a particular biological situation, that new population of the birds which appeared near Moscow, and this new gene started to propagate with a speed, roughly speaking, about 50 kilometers per year. It was written in the biological introduction to this Kolmogorov Petrovskii Piskunov paper. But this population, in fact, as showed a recent analysis, has very complicated structure. This structure is intermittent. We can divide all this Kolmogorov Petrovskii Piskunov circle, or the radius r of t, into several rings. And in the outer rings, we have very sparse populations, subpopulation with a high density. In the next, it means that if you consider number of the particles in 1 square kilometer in the outer ring, that expectation here will be some constant density near the boundary, but second moment here will be necessarily very high. This is the intermittency. In the next ring, first and second moment will be, third moment will tend to infinity, and so on and so forth. This, in fact, this phenomenon of intermittency is very typical for many biological processes, including, for instance, spreading of the COVID and so on and so forth. I have to stop here.
Another 5 minutes.
Okay. What?
Another 5 minutes.
But you said me 5 minutes 5 minutes ago. I want I respect the.
I said approximately 5.
Okay.
About 8,
No.
7, 8.
It's better to stop here.
Oh, thank you very much for
No.
any questions.
At least I try to, I don't know how successfully, to be more or less popular, but maybe it's not easy. Yeah.
Why are some stars hot and some cold?
What?
The same plasma. The plasma is the same. Yeah, the question is, why are some stars hot and some other stars are cold? Because the plasma is the same. So who decides what the value of
No, look.
mu is for a given star?
The cooling of the star related, first of all, to the thermonuclear processes in the start. It's according to a popular theories. First of all, there is thermonuclear reaction, like in hydrogen bomb. But when that hydrogen more or less will disappear, first of all, it will significantly shrink this. But it's still, each star contains some other elements. Gallium, for instance, which is not included in any thermonuclear reaction. This is a different story. We are talking only about intermittency in the photosphere related to the fact that columns, convection columns, can disappear. Why they disappear? Not clear. Why in the what we call today, it was little ice age from 15th century, roughly speaking, to the middle of 19th century, when, according to statistic by Maunder, number of the black spots starting from 15th century decay like linearly and reach practically zero to the beginning of the 17th century to the central part of so-called Maunder cooling or Maunder minimum, but no at all. Why it happens, nobody knows. Why it happens, large snow, large ice age, is nobody knows because, yeah. Yes.
Oh, okay. Well, I was going to ask exactly that. I mean, is there any way to connect the Maunder minimum to some kind of intermittency, or is that also?
I don't understand. Do you understand?
What is the link between Maunder minimum and the intermittency? Between Maunder minimum and the intermittency. Is there any link between these two things?
No. Explanation of the, there is no explanation of the minimum.
Okay.
It's there was only explanation that small number of the, what I try to explain using idea of Zildov, the small number of the black spots is the indication of low activity. There is no enough transport of the hot plasma from the inner part of the.
Yes, but it's lower activity, but the question is about intermittency. So you say low or high?
Yes, but look.
Intermittency and minimum. Is there
Yes, but black spots are distributed highly non-uniformly. That they, it means that convection columns distribute highly non-uniformly. There are areas when we have several black spots at a small distance, and there are large areas without. This is already intermittency. There is intermittency in the distribution, but it's again and
right now, the activity of
Democratize.
black spots, is it average, so it's growing, or is it compared to say 1,000?
look, this is, yes. I'm not expert, but I believe that after middle, so-called little ice age finished, according to all sources with information, it's about 850. And after this, number of spots started to increase. But on the Earth, there are now another, maybe more powerful factors acting on the climate and so on and so forth. But what is very well known, that at the time around 1000 years AD, 9th century, 1000th century, that climate was essentially more warm than even today. There is classical example. There is Wrangel Island, north of Bering Strait. It's typical polar region. It's covered by the ice and snow of the full year. But modern excavation shows that the taiga covered this in the 8th century AD. Taiga covered all this island, and mammoths existed. They degenerated a bit, like small elephants, but they existed. It's they have the size of the cow. It's very recent. It's one of the 2 years ago journal Scientific American. I read very interesting paper about this excavation on the island. Climate was much more warm, and the same situation probably was in Europe, in Greece, Italy, and so on and so forth. After there is no complete return right now, some areas of the polar ocean already clean from the ice. But navigation along the North Asia is not possible even in summer. There are ice somewhere. There are clean areas, but polar ocean was cleaned from the ice in the time about 1,000 years AD. This is some events which nobody can explain. What is the
fluctuation?
no fluctuation, but is they extremely large? Yes. It's not the fluctuation. It's not astronomical fluctuation. Not because the orbit in Arnold papers is written that that size of the Earth's ellipse can increase in 200,000 years 3 times. Of course, it will be disaster. That's it will be extremely cold. But this is astronomical. But we are talking about events in the very small time scale, 100,000 years. That's it. Okay.
Any other questions?
Thanks for the nice talk. So I was going to ask about the population dynamic models, branching Brownian motion thing. And is there also analogous phase translation for in terms of the lambda parameter, where above this threshold you have this exponential growth for the second moment, and below you don't?
Repeat one more time. I didn't.
So I was asking about the. So you have shown the second moment grows exponentially if you have a large or small v. Is there a similar phenomena for the branching Brownian motion model you mentioned?
Yes. It's the same situation. Equation for the population dynamics are the same as equation for magnetic fields, but only they scalar. But if you consider population dynamics with several types of the particle, it will be complete similarity with the magnetic field. You have vector valued.
So second moment can be bounded.
Second moment can be bounded,
Okay.
yes.
Yeah. Okay. Yeah. Thank you.
Any other questions, please?
In Kolmogorov Petrovskii Piskunov model, second model is bounded outside this circle. When there are some particles outside this circle, as I told you, definition of this radius R of t depends on what kind of population we must include. In parabolic system, parabolic particles move with infinite speed. They can be everywhere with very small probability, of course.
No more questions. Okay, then let us thank the speaker again.
Thank you.
Let me remind you that on Thursday, Professor Molchanov will start a course a bit more mathematical. So, but anyway, in the same direction, something on intermittency on fractals. So, of course, everybody is much more welcome. And as I understand, there is some reception today. So again, everybody is welcome.